Hello and welcome. This is going to be our lecture video for May 13th. I'm going to be reviewing exponential and logarithmic functions today, as well as a little bit of rational functions. Let's get started with this problem here. How much better is 1% interest each month for a year compared to 12% interest at the end of the year? So the 1% is better because it allows compounding to happen. But can we say how much better it is? Well, let's remember how we write out this growth here. So if I'm going to take my principal and grow it by 1%, I need to multiply it by 1.01. Add in this extra 1 here because this one allows you to get your full amount back plus an additional 1%. After you grow 1%, you are now worth 101% of the previous value. All right, then if we're going to grow again, you can multiply again by 1.01, then again by 1.01, 12 times. This is going to become the principal times 1.01 to the power of 12, or the principal times, let's do this in our calculator, 1.01 to the power of 12 is 1.1268. Versus, if I grow just 12%, that would be just times 1.12. So times 1.1268 is bigger than times 1.12, and it's specifically 0.0068 times bigger. Or we could say it's 0.7%, round up a little bit there. So, for each $100 we deposit, we get an extra 70 cents at the end of the year by doing the first investment strategy. All right, goal today is to review exponential and logarithmic functions as well as rational functions. Why are we doing this? We are reviewing all of our second semester units to cap off the year. All right, here's a problem for you to practice with. I recommend you trying it on your own real quick. And now I'll show you how to do it. So I've got a variable on both sides in the exponent. I need to get the bases to match so that I can get these both out of the exponent, because I can't really use logarithms yet. It won't free both of the variables. I need to get the bases to match. So it's very helpful that both of these bases can be written with the same base. They can both be written with the base of 4. 4 to the third is equal to 64, and 4 to the negative 2 is equal to 1 over 16. So now I can rewrite this as 4 to the third to the negative x, and this side as 4 to the negative 2 to the 2x plus 1. Now when you've got a stack of exponents, you can multiply that stack. Be sure to distribute the negative 2 here, and we will get 4 to the negative 3x equals 4 to the negative 4x minus 2. Now in this next step, we can say that we're taking log base 4 of both sides, or you can just say for these two sides to match, it would make sense that the exponents would have to match as well. That's the only way you're going to make these two sides match, because they both have the same base. All right, so let's set these exponents equal to each other. We've got now 3x equals negative 4x minus 2, so negative 3x equals negative 4x minus 2. Add 4x to both sides. And just like that, we're done. X equals negative 2. You can plug it back in to double check, and I think you get 4,096 equals 4,096. All right, next one. Here we only have the variable on one side, so we can use logarithms here. I'll show that over here. We would do log, the base of the exponent becomes the base of the log, and then the exponent and the number on the other side switch spots, so log base 2 of 1 equals negative a. In the older calculators, you can plug this in by doing log of 1 divided by log of 2, and I get the number 0, which actually makes sense. Any log base anything of 1 equals 0 equals negative a. Divide both sides by negative 1, we just get a equals 0. The other way to solve this would be to express this 1 as a 2 to the 0th, then drop the base on both sides, negative a equals 0, a equals 0, It's about the same number of steps each side, but this side didn't require a calculator. All right, problem 44. We need to graph this. So I need to remember that this number in front is my starting value, or it's like the starting height of Alice, and this is our vertical shift. So we could say this is the table Alice is standing on. This is the first thing I want to add to my graph. I want to add that horizontal asymptote. All right, so the vertical shift is -2. Normally, these graphs flatten out to 0, but this one's going to flatten out to -2 because that is the vertical shift. Now, Alice is 5 feet tall at the beginning. So she needs to be 5 feet above the table. So that would put her head up here at the 3 mark. Now, this is the strength of the shrinking beverage. So she's getting half as tall each time we move one to the right. So 1/2 as tall. So she was 5 feet tall. Now she's going to be 2.5. Measuring up from that blue dotted line, that put our dot right there. Then it'd be 1.25, then 0.6, 0.3, 0.15. And by this point, we're so close to that line, we can hardly tell the difference. And then going the reverse direction, if we're getting cut in half to move this way, we're going to double to move this way. So if she was 5, now she's 10. Measuring from the table, that brings us up to 8. Next, she'll be 20. Measuring from the table, that brings us to 18. So her height went 20, 10, 5, 2.5, but the vertical shift moved everything down 2 units. And that's what our graph looks like. It shoots off to positive infinity this way, and then in this direction it levels off to -2. Never exactly equaling -2, but just getting closer and closer. All right, another money problem. So you deposit $4,000 into an account that earns 9% annual interest. You leave the investment for 8 years. Given the different circumstances, what's the final amount that you're going to have? So simple interest says, okay, 9% for 8 years, 9% times 8 years. We're going to ignore compounding and just say that getting 9% for 8 years is basically like getting 72% one time. So that means I'm going to take my 4,000 and I'm going to multiply it by not 0.72 but 1.72. We often forget that 1, but we got to get our full amount back plus the additional 72%. So 4,000 times 1.72 gets me a final balance of 6,880. All right, compounded semi-annually. So semi-annually, this is n equals 2 scenario. So this says, okay, we're going to advertise 9% annual interest, but we're going to pay that out as a 4.5% interest at 6 months, and then another 4.5% at the end of the year. What this is going to look like mathematically, I'll write it down here. You're going to take your 4,000, you're going to multiply it by 1 plus, I forgot to write the 1, 0.09 divided by 2, so that splits our interest into 2 payments, to the power of, we say NT, so 16, because if you get 2 payments per year for 8 years, that's a total of 16 payments. This whole thing can just be plugged into your calculator. I'm going to do the 1.045 to the power of 16 first, then multiply it by 4,000, and I get quite a bit more. I get $8,089.48. So that compound interest really helped us out over the 6,900, where, $1,200 more, because our money was able to compound. All right, let's see if we can get even more money by compounding more frequently. Monthly means n equals 12. So same formula, but we're splitting those interest payments into 12. So 0.09 divided by 12 to the power of 12 times 8. 12 times 8 is 96. So 1 plus 0.09 divided by 12 equals 1.0075 to the power of 96. I get a number a little over 2 times 4,000. And I do get more money. Now I'm up to $8,195.68. So not like a ton more, but a little over $100 more by compounding monthly versus semi-annually. Now compounding continuously has a completely different formula. This is final amount A equals PE to the RT. All right, let's just plug in what we know. 4,000 times E. E is just this number. It's 2.71. It's in your calculator. The rate we'll express as a decimal, 0.09 times the number of years, so times 8. All right, so e to the power of 0.72 times 4,000, and this gives us our most money yet, $8,217.73. So that means every second of every day the money is growing at a rate, and that rate adds up to 9% over the whole year. Okay, another practice problem. How do we solve this one? This would be a really good one to pause and just try on your own, since it's very similar to one we already saw. A equals 70 divided by 5 is 14. Base of the exponent becomes the base of the log. These numbers switch places. This has got a value, but I'm going to go ahead and divide by 7, so I can just plug this all into my calculator at once. 15 divided by log 15 divided by 7. And I get A equals 0.13922. All right, and this is irrational. If this is asked on a test, you will most likely be asked for a specific number of decimal places, or it'll be multiple choice. All right, another one to practice. Another good one to pause and try on your own. This time we have to rearrange our logarithm the other direction. So you can do the swoop like this. 9 squared equals negative b. 81 equals negative b. B equals negative 81. All right. This one, we don't have the prompt, but most likely we're being asked to simplify. Simplify. So that means we're going to use our properties of logarithms. One is that coefficients in front can become exponents. So this can now become log base 3 of u cubed minus log base 3 of v cubed, and then subtraction between two logarithms with the same base can become division within the argument. So just log base 3 of u cubed over v cubed. I'll leave it like that. You could take the cubed out. You could do, yeah, but that's fine. As long as you're able to just work with the properties, you'll be able to always pick the right answer. Okay, here what's one that requires the properties, and then we're going to have to solve. So we can put these together using that division. So this becomes log base 6 of x plus 5 over x equals 3. Now we do the swoop. 6 to the third equals x plus 5 over x 6 to the third is 216. I'm going to move that x over by multiplying both sides by x, so now it's 216x equals x plus 5, subtract an x from both sides. So now it's 215x equals 5 divided by 215. And I'll convert this back to a fraction to get 1 over 43. So moving on to rational functions a little bit. We've got a rational function, identify the points of discontinuity, holes, vertical asymptotes, x-intercepts, horizontal asymptotes in the domain. So all of that, in order to be able to do that, well, before we factor, we can actually figure out a few things. One thing is the y-intercept. The y-intercept is right here at the end. It's when every other term except for the constants go away. Our y-intercept is equal to 8 over 3, which is 2.6. Put a dot right there. Another thing we can figure out is the end behavior asymptote. We have to look at the degree of the top and the bottom. The degrees match. So the horizontal asymptote will be at the ratio of the leading coefficients. So negative 2 over 1, which just becomes a negative 2. So our horizontal asymptote is the line y equals negative 2. We can go ahead and add that in. All right, now to figure out other features, we do have to factor the top and the bottom of this. So let me see. Let's see. I can take a negative 2 out of the top, leaving behind an x squared plus 5x plus 4. And on the bottom, this is ready to be factored into, let's see, two numbers that multiply to be negative 3 but add to be 2 are a positive 3 and a negative 1. All right, let's finish factoring the top there. So negative 2 times, now I need two numbers that multiply to be 4 but add to be 5. That's going to be a 4 and 1. All right, nothing cancels, so we have no holes. And then these values on the bottom give us our vertical asymptote. So we're going to have a vertical asymptote at negative 3. So it's the value that makes it equal to 0. And 1. All right, go ahead and add those in. Negative 3 and 1. And then the values that make the top equal to 0 are my x-intercepts. So x-intercepts are negative 4 and negative 1. So negative 4 and negative 1. And we've got that point there. The domain would be x equals all real numbers, except x cannot equal the vertical asymptotes negative 3 or 1. And I think we've covered everything now. So let's just connect up these points. So here comes in our graph. It wants to stay close to that horizontal asymptote until it reaches this wall. It has to go over. If it goes up to infinity, it's going to disappear, reappear. It's going to hit this point here, travel up, disappear, reappear, and then loop on out of here. All right, so a rough sketch, but showing all of the features. Another one, to graph and state the equations of slant asymptote. So we know this has a slant asymptote because the degree of the top is 1 more than the degree of the bottom. So we're going to go ahead and do long division. X squared minus 16 divided by 4x plus 8. 4x times what equals x squared? That's going to be a 1/4 x. Now we're going to complete the multiplication. We'll get the x squared. We'll also get a plus 2x here. Subtract this away. Now we've got negative 2x minus 16. What do I have to multiply 4x to make it a negative 2x? Well, it's going to be a negative 1/2. And at this point we stop. That is the equation of our slant asymptote. y equals 1/4 x minus 1/2. So let's put a point at negative 1/2. We're going up by fourths, so that means now we're at negative 1/4, then right there, then up 1/4 to get our next point. We're down 1, left 4. There are all the points on our slant asymptote, so I'll connect these up with the dotted line. Let's see, the top can factor into an x plus 4 and x minus 4, so those give me my x-intercepts. The constants give me a y-intercept of negative 2. And on the bottom, let's see if I set that equal to 0, I'll get x equals negative 2 is my vertical asymptote. All right, connect up all the dots. And lie tangent to the asymptotes. And we get a graph that looks like this in red. Okay. Here we've got a rational function to simplify. So if we're simplifying, we're looking to maybe cancel. So let's see if this top factors two numbers that multiply to be negative 24 but add to be negative 5. Those are going to be a negative 8 and a positive 3. And then the n plus 3 can cancel. And now I've just got n minus 8/4. And then we still want to say n cannot equal negative 3. Just as a reminder that if it did, we'd be dividing by 0, even though this factor canceled out. All right. So exit ticket is to go work on the homework that's attached to today's date on the calendar. And then have a good rest of your day.